Hey there, my name's Gary Sims and this is Gary Explains. Now with the announcement of the OnePlus 7 Pro, there has been lots of talk about 90Hz displays. Now the OnePlus 7 Pro is not the first Android device with a higher than 60Hz display, however it has brought this subject to the foreground. And today I want to talk about refresh rates, frame rates, SurfaceFlinger, display processors and much more. Now if you want to find out how it all works and what it all means, please let me explain. So let's start by defining refresh rate. Now the refresh rate is how often the display turns on and off those pixels to show you one particular frame of data. So a normal Android phone probably does that at 60 Hz. So 60 times a second, the display will physically redraw all those pixels to show you what's going on your device. Now, other displays can work at 90 Hz or even 120 Hz. That means that in 1 second, rather than redrawing all those pixels 60 times a second, it will do it 90 times a second or 120 times a second. So the physical display updates itself 90 times a second with this display that we find in the OnePlus 7 Pro. But it has to be told what data to display. So in that sense, it's a consumer of the data from the Android device, and then it updates itself according to its refresh rate. But the thing that just supplies that data is the CPU and the GPU. So for example, if you are doing any kind of gaming or if you're using the user interface, the CPU and the GPU need to calculate what's coming up next on the display. Where is that particular icon going to be displayed? Where is that particular sprite going to be? What is this current movie frame that you are watching? And then basically the CPU and the GPU tells, and I'll tell you how it does that in a second, but it tells the display, please display this frame of data. Now, of course, the rate that the display is consuming the data and the rate that the CPU and GPU are creating the data are two different things. So the refresh rate is the rate that the display is consuming the data, and the frame rate is the speed at which the CPU and GPU can produce that data. Now, in between the CPU and GPU and the actual display, there are a couple of important components. The first one is a piece of software called the SurfaceFlinger. Now, this is part of Android, and its job is to get together all the different bits of information that need to be displayed and send them on their way towards the display. Now, a typical display on a Android phone has many layers. So, for example, the status bar that you see up at the top of your device is often shown even when you're inside of a different app, and it's pretty static. It's up there, it may have a notch, it may not have a notch, it's got the clock, it's got kind of other things up there, and that is really one layer. And the navigation keys that you'll get at the bottom of the screen, if you've got on-screen navigation, is a separate layer. And sometimes these change as well, depending on, the orientation and things like that. So that's two layers. And then often you get the content in the middle, which is the app that you're using, which is a third layer. And the SurfaceFlinger takes these surfaces, takes these layers, and says, now let's put them all together and then send them out to the display. Now the SurfaceFlinger doesn't actually try to do that overlaying of those different layers, that composition itself. It relies on a piece of hardware which is called the display processor. Now all smartphones have a display processor today, and they are experts at taking bits of data and then squashing them all together to make one frame that's ready to go out to the actual physical display. And in doing that, it can do things like color blending, and it can do alpha channels, and it can do rotation, and it can do all this kind of stuff. And it's very, very quick at grabbing, let's say, the data from the video decoder and the UI and the status bar, and it brings them all together, creates one sandwich and sends that out to the display. ARM actually have a range of display processors which are called the Mali-D something or other range. And recently, actually, ARM just announced the Mali-D77, which I'll talk about in a minute, which is their latest display processor. Now, as I mentioned, the display is a consumer of the data, and then the CPU, GPU, with the help of the SurfaceFlinger and the display processor, are the producers of that data. Now, if these two things aren't synchronized, you can get one of two problems. If the data isn't being produced fast enough, what happens is the SurfaceFlinger says, well, you haven't given me a new layer for that piece of content, so I'm just going to use the old layer and just send that out to the display driver. So while the display driver will never show, just a black part of the screen because it's empty, it will just show what was there before. But of course, when we're looking at it, we can actually see some kind of lag because we saw all this nice smooth animation, our game was running really nicely, and then suddenly it seems to have a bit of a lag because it pauses for a moment. And that's because the SurfaceFlinger was not getting enough data from the CPU, GPU, and it had to just display what was there before. And of course, to us, that looks like it froze. Even just for a moment, even just for a fraction of a second, we see that pausing. And the opposite can also happen. If the frames are being produced greater at a faster rate than what the display can actually handle, then frames need to be dropped. So in this case, the app becomes frame rate capped. That means that the actual frame rate is higher than what the display can handle. And of course, the display is the ultimate physical barrier. If it can't handle that data, the new frames get dropped, but you still maintain 60 frames a second or 90 frames a second if it's a 90 Hz display. But the capping, the limit then becomes that physical display, what it can handle. So from a software point of view, how you synchronize what's being produced and what's being consumed happens in several different ways. The simplest approach is just to use a loop where the app produces the next frame, it passes it on to the SurfaceFlinger, and the SurfaceFlinger takes it as quick as you're giving it and then passes it on to the display. Now at some point maybe the SurfaceFlinger will say, I've got no more buffers left over, I've got no space for you to give me the next frame, so please just wait. Just stay there a second until I've dealt with this latest buffer, and then you can give me the latest bit of data. So when you're doing that way, you're always guaranteed that you're running at the maximum speed that the SurfaceFlinger can handle. There are some problems with that approach, but we won't go into that now. A different way of handling it is that actually there is this thing called the VSync, which is the signal that fires off the SurfaceFlinger that it kind of gets in synchronization with the display so that it knows that the display is soon going to be wanting to take a new frame of buffer. And that VSync can be exposed through the choreographer framework inside of Android. And so a game can actually time its frame generation based on the choreographer framework and the signals it's getting from that synchronization between the display and the display processor and the SurfaceFlinger. And a third way of doing it is just to use a timer. Every so often, fire up a piece of code that will generate the next frame for the SurfaceFlinger, the display processor, and then onto the display. So if we're talking about timings, let's just think about this for a moment. If we're talking about 90 frames per second or 60 frames per second, if you measure that in milliseconds, 1 second is 1,000 milliseconds. So if you do the maths, if you want to actually get 60 frames a second out to your display, you need to produce a new frame every 16 milliseconds. So 16 milliseconds has kind of been this golden standard for apps to produce the next frame to make sure the content is smooth and you don't get any dropped frames and you don't get any lagging. Now, of course, when you go from 60 Hz to 90 Hz, that's a 50% increase. And conversely, when you go from 16 milliseconds, you actually get it down to 11 milliseconds so that you can produce all those frames. That's a 30% decrease. So what that means is that the app has now got to generate those frames quicker. 30% less time is available for it to produce each frame. And that's why you hear people talking about it's going to be optimized for 90 Hz displays, because actually what they mean is we've got to make sure that we can get 90 frames a second, reduce our calculation slice to 11 milliseconds for each and every frame. Now, when we talk about VR and AR, actually a lot of the headsets have already moved over to 90 Hz displays and things are really heading towards 120 Hz displays. Now, I mentioned the new Mali-D77. It's the latest display processor from ARM that's got extra functionality specifically for VR and AR displays at 90 and 120 Hz. So for example, when you look at a VR headset, the screen is very close to your eyes. And so you have to have some lenses between your eyes and the screen to make things look like the immersive world that we find in AR and VR. And that means that what's projected onto the screen needs to have lens distortion built into it, so that when it goes through the lens, it appears correctly to your eyes. Now at the moment, that lens distortion is calculated by the CPU and the GPU, pass through the SurfaceFlinger into the display processor and then onto the display. But the new Mali-D77 understands the concept of a lens. So you can pre-program it to say, actually everything you pass on to the display, please make sure it's got this lens distortion pre-applied to it. And that frees up the CPU and the GPU from having to calculate that lens distortion. Another clever trick that it has is something called asynchronous time warp. And what that means, if you imagine a kind of a VR or AR headset, as you're moving your head, the picture is moving, but it's not being replaced. It's just the same picture, maybe twisted or manipulated in a certain way, depending on the angles that the sensors in the headset are sending to the CPU and GPU. Now, up until now, that recalculation is done purely on the CPU and GPU. So the new sensor data comes to the CPU and GPU, it works out that you've moved your head, it works out how to redraw the scene. However, when we are looking at VR and AR applications, you can get motion sickness if the display doesn't keep up with what your head is telling it. Because when your body, your brain, head feels that one thing's happened, but your eyes are saying another, that's when you get motion sickness. That's why we get seasick as well when we go to on a boat, but that's a whole different discussion. Now, what this means is that if we can smooth out that delay between what the GPU and the CPU are calculating and what the eyes are seeing, it will reduce or even eliminate motion sickness. So the Mali-D77 can do this asynchronous time warp in that using the data it already has in the buffer, it can twist it and rotate it so that actually it's matching what the sensors are doing in the headset. And then a fraction of a second later, the GPU and CPU will send a new frame and they will fill in all the bits and it will be a new calculated frame. But if we're running at 120 Hertz or 90 Hertz, sometimes the GPU and the CPU can't catch up, but the display processor is able to fill in the blanks because it knows what will already be displayed, it knows how much you've tilted your head, and so it can tilt the image accordingly and therefore make the overall experience much smoother. So display processors are actually a really key part of this whole chain of CPU, GPU right through to display. In fact, ARM reckon that if you take away the lens distortion and add in the time warp functionality, you can take away as much as 15% of the workload from the GPU, which of course gives it extra time to produce a higher frame rate and therefore improve the overall VR AR experience. Okay, so what have we learned? Very quickly, the refresh rate is how fast the display can physically redraw its display. The frame rate is how fast the CPU, GPU can actually produce the content that's going to be displayed. The SurfaceFlinger and the display driver are the glue in between what the CPU and the GPU is making and what the display is displaying, allowing that data to be sent from one to the other, including composition, laying the layers on top of each other, and even in a VR and AR situation, actually manipulating that data so it's correct for a headset, or if it's just a normal smartphone, it's actually correct for what we're seeing on a smartphone. Okay, that's it. My name's Gary Sims. This is Gary Explains. I really hope you enjoyed this video. If you did, please do give it a thumbs up. Don't forget to subscribe, and well, that's it. I'll see you in the next one.